Hi, I'm Mark with Mastercam, and in this video I'd like to show you a couple examples of how 3D tooling can be used to help make programming your parts easier. On this part, I'm using a dynamic lathe operation that is cutting out a channel. The tool for this operation was created from a DXF file that was downloaded from a tooling vendor's website. When I backplot the tool path, we can see the tool holder hits the part. Because the custom tool being used is only a 2D representation, Mastercam isn't aware of the curvature of the holder. What we can do to fix this issue is create a 3D tool. I can launch the tool designer by going into the lathe tool manager and right-clicking in the part or library windows, or by opening the parameters for my tool path and right-clicking in the tool display window. Once the tool designer opens, I need to give the new tool a name, select the type of tool from the tool type dropdown, and set an offset number. On the insert page, I need to select the step file that I want to use for the shape of my insert. And I need to define the corner radius, which I can enter manually or select from the model. Using a 3D insert means that Mastercam can properly represent the relief angle of the cutter in backplot and simulation, which you can't do with traditional 2D lathe tools. On the holders page, I select the step file that defines the shape of my holder. I also need to define the machine connection plane, which is the rear face of this holder. Using a 3D holder means that Mastercam is now aware of the true shape of the holder, so false collisions like the one we looked at earlier are no longer an issue. Additionally, this means that collisions we may not have seen in backpart simulation due to an underdefined tool holder are no longer an issue either. For this example, I don't need to make any changes on the mating page, but if the tool and the holder were not aligned properly, this is where I could correct that. On the setup page, I need to define the cutting plane. In the machine orientation page, I can define the tool orientation, which turret it's loaded in, and the spindle direction. New in Mastercam 2020, the tool designer will automatically populate the compensation page based on the tool geometry and the machine orientation settings you defined. At this point, I can click the green check to finish creating my 3D tool and select it from my tool path. Once the tool path is regenerated, I can launch backplot, and the tool is now properly represented, which means the false collision is no longer displayed. Another example where 3D tooling is helpful is with face grooving. In this example, I have a shaft with a face groove that is using a center for support. If I tried to program this tool path with a standard 2D tool, there is no way I would be able to get the precision I need or be able to accurately backplot or simulate this toolpath before posting it out. Thanks to 3D tooling, I can accurately represent a complex tool such as the one I'm using and get the results that I need. Hi, I'm Mark with Mastercam. In this video, I finished up all the programming on the first side of the part. Now it's ready to be flipped 180 degrees so that I can program the operations to cut the other side. The first thing I need to do is create a stock model. On the stock definition page, I'll give it a name, define the initial shape and the size. On the source operations page, I'm going to select all my previous operations by clicking on the machine group, then clicking OK to generate the model. Once the stock model is generated, I need to convert it to a P-mesh. Now that I have an accurate representation of my stock up to this point, I need to rotate the solid model of my part as well as the stock model 180 degrees. On the Transform tab, I'll launch Rotate and select the P-mesh and the solid for my part. I'll enter 180 as the angle and reselect my rotation center point. To make the graphics less cluttered, I've chosen to rotate the part so it doesn't overlap the original solid model from my first setup. On the Advanced tab, I'm going to enable new attributes and enter 800 so my transform geometry is placed on level 800. Now that my geometry has been rotated, I can turn off all the levels except for level 800, where my new geometry is located, and add a new machine group. On the Machine tab, I'm going to select the machine I'm using from the mill turn dropdown. Normally, I would load a Haas ST20 from the lathe dropdown, but since I have the additional mill turn machine environment for it, I need to go to the mill turn dropdown. Having the mill turn machine environment means I have full machine simulation, which is extremely helpful when programming. I need to select my part geometry and have Mastercam create a turn profile and place it on level 820. For bar stock, I'm going to set the geometry type to STL, then select the P-mesh I rotated earlier. Lastly, I'll define the stick-out amount by selecting this face on the part, and then I'll make that value slightly larger to make sure that there's a little clearance between the jaw and the face. At this point, I'm ready to cut the backside of my part, and thanks to just a few minutes worth of work, all my operations will be stock aware. Hi, I'm Mark with Mastercam, and in this video I'd like to show you how the mill-turn machine environments for 2- and 3-axis lathes can make it faster and safer to program thanks to the enhanced machine simulation. Here I have a Haas ST20 SSY lathe which is running in mill-turn simulation. Being able to work in the mill-turn simulation means I can simulate all the machine components, work holding, stock, tools, and tool holders. In the Operations Manager, I'm going to select all my operations, then click the G1 button. Normally, the G1 button would post out the code for the selected operations, but since I'm using the mill-turn machine environment, the G1 button launches the Sync Manager instead. If I were programming for a multi-stream machine, this is where I would synchronize my operations to avoid machining errors or collisions due to conflicting turret movement. Since the Haas ST20 is a single-stream machine, I'm going to use the Sync Manager to post out my code when needed and launch simulation. If I was to look at the operations I selected in simulation, I can see that the tool for operation 29 is too short, so the turret and the tailstock would collide if I were to run this at the machine as it is right now. This is a perfect example of why it's so important to review your toolpaths and backplot simulation before posting them out. This issue would not have shown up in backplot, since it's a collision between machining components, which backplot isn't capable of displaying. Taking a few extra minutes now can save you from ending up with a broken tool, a damaged machine, or simply having to diagnose an unexpected stop. To fix this issue I'm seeing in simulation, I need to increase the projection for my finishing tool. To do this, I'm going to switch back to my main Mastercam window. In the Toolpath Manager, I'm going to click the Tool Setup button. Inside the Tool Manager, I can right-click on Tool 16 and select Set Projection Length. Then, all I need to do is click and drag the arrow to adjust the projection length. I want to add an extra ½ of an inch to my projection. So to make it easy, I can keep my cursor over the ruler while dragging, and the projection value will snap to specific increments. I can now press Enter to save my changes, close the Tool Manager, relaunch the Sync Manager, and look at my operations and simulation to verify I no longer have a collision.